Hi everyone, welcome to G14, which is a very short and compact unit on similar figures. Now I know we've done similar triangles and we talked about similar parallelograms and that kind of thing, but this time we're talking about similar solids. So we're talking about similar 3D figures, so three-dimensional figures here. So this kind of plays off a lot of our surface area and volume from back in G13. So let's get started. Here we go. First, we're going to start with what the definition of a similar set of figures is, okay? Similar figures or solids are similar if their linear measures are proportional. Their linear measures are proportional. So now we got to talk about what that means. There's two words here to really key in on. Linear measures, and we're back to this idea of proportional. So we're going to play a lot with what we already learned with similar figures, but now we have to expand that understanding to a third dimension. However, we're really going to be focusing on and really need to understand what a linear measure is. So let's keep going, and here we can compare. It says, compare the ratios of the area of two solid figures, so the area of two solid figures, by squaring their linear measure. So if you have something that's a linear measurement, let's say there's a ratio of two things, A to B. This is a linear measurement because this might be, for example, 1 centimeter versus 8 centimeters, 1 to 8. That's a linear measurement, a length, okay? Well, to compare their areas, we have to look at centimeters squared. So we have to square the linear measures. And to compare the ratios of two volumes, we would have to cube the linear measures. In other words, if you have a scale factor of something in linear measurement, to jump from linear measurement to an area, you'd have to square those measures. And to jump from linear measurement to volumes, you'd have to cube those measures. So let's see what it might look like here when we're talking about two cones. The ratio of these two cones, okay, might be, let's just say that R1 is 3 inches and R2 is 6 inches. So the ratio would be 3 to 6, which would reduce to 1 over 2. Well, their areas are squared measures. So here I've got the A versus B as 1 versus 2. So the A squared versus B squared would be whatever 1 squared is versus 2 squared. Well, 1 times 1 is 1 and 2 times 2 is 4, so this ratio is 1 versus 4. Let's go one more layer. Come on down here to volume. A cubed versus B cubed. Well, if the A is 1 and we're cubing that, and the B is 2 and we're cubing that, 1 times 1 times 1 is 1, and 2 times 2 times 2 is 8. So the volumes would have a ratio of 1 to 8. So all three of these use the exact same linear measure, but we're changing it based on what dimension we're working in. When we're measuring a length, that's 1 dimension. When we're measuring areas, that's 2 dimensions squared. And we're measuring volume, that's 3 dimensions. Let's do a little practice with this. See what I mean? Here we're given the ratio of corresponding segments. This is 1-dimensional. This is linear length. If I measure a segment, we're going to compare that to the ratio of the areas, which is 2-dimensional, and also to the ratio of the volumes, which is 3-dimensional. So if my area, or if my segment length ratio is 3 to 4, to get the area, I would square that value. So 3 squared and 4 squared would give me an area ratio of 3 times 3 is 9, 4 times 4 is 16. To get a volume ratio, I would take this A and B, these two values here, and I would cube them. 3 cubed over 4 cubed. Well, 3 times 3 times 3 is 27. 4 times 4 is 16, and 16 times 4 is 64. So these three ratios all represent the same image. We're just giving a ratio of linear measure, area measure, and volume measure. All right, let's try again. This time, the measure of the segments has a ratio of 2 to 3. So my A is 2 and my B is 3. So to turn that into area, we need to square it. 2 squared versus 3 squared. 2 times 2 is 4. 3 times 3 is 9. To turn this measure into volume, we'd have to cube the values. 2 cubed and 3 cubed. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. All three of these ratios represent the same figure. It's just representing it in different dimensions. Take a moment and try example 3 and 4 on your own. Okay, let's compare. In number 3, if our linear measure is 1 to 5, then our area ratio is 1 to 25. So while the segment may be 5 times longer, the area is 25 times bigger, and the volume is 1 to 125, so the volume is 125 times bigger. All right, check number 4. The linear measures are 5 to 8. Square them, and you'll get an area ratio of 25 to 64. Go back and cube them, and you'll get a volume ratio of 125 to 512. Okay, next, the given is a little different. Check it out. This time, we've been given our information in area, which is a two-dimensional measure. So what you have been given is A squared versus B squared. So we got to work backwards, okay? In order to get our linear measurement, we need to take the square roots of these two values. The square root of 9 versus the square root of 25. Well, the square root of 9 is 3, and the square root of 25 is 5. So this ratio is 3 to 5. Here we're doing the inverse order. We're moving from something that's squared to something that's linear. Now that we have that linear measure, we can manipulate that into a volume ratio. So we have to take our linear measure, 3 and 5, and cube it. 3 times 3 times 3 is 27. 5 times 5 times 5 is 125. Let's skip down here to number 8 and practice that again. In number 8, let me move this down a little. There we go. In number 8, we've been given the area ratio as 81 to 1. That means these are our A squared to B squared values. These are our square ratios. So we got to backtrack. We got to go back up top. To undo a square, you need to square root these values. So the square root of 81 versus the square root of 1 is 9 to 1. Once you have that linear ratio, then you can bring it down to turn it into a ratio of volumes. volumes mean cubing the linear value. So 9 times 9 times 9, which is 9 cubed, is 729. And 1 times 1 times 1 is just 1. I think the ones that have a 1 in them are pretty cool. They're a lot easier to understand for me. This is saying that one segment is 9 times longer than another, which makes the area 81 times bigger than the other, which makes the volume 729 times bigger than the other. It's pretty cool. All right, we have 2 more to look at. In these 2 examples, what has been given is the ratio of volume. So what is given is your cubic measurements. Well, there's no way to go from cubic measurements to square measurements. You've got to go all the way back up to the top. You can turn your cubic measurements into linear measurements by taking a cube root. A cube root. If you need help finding that button on your calculator, let me know. What you're asking is, what multiplied by itself 3 times gives us 64? And if you check this out in the chart, we've done this before. 4 to the power of 3 is 64. So the cube root of 64 is 4. And 3 to the power of 3 is 27. So the cube root of 27 is 3. So we took this ratio of volumes and dialed it back to the linear ratio by cube rooting. That is the inverse of cubing. Now we can move forward to find the area ratios. To go from linear to area, we square. So 4 squared versus 3 squared. 4 times 4 is 16. 3 times 3 is 9. Give number 7 a shot all by yourself. See what you think. All right, let's compare work. I took 1 over 216 and I reversed that cubic ratio into a linear ratio by cube rooting the values. The cube root of 1 is 1. The cube root of 216 is 8. Then I can move forward again. I can turn this linear ratio into an area ratio by squaring my values, and that gave me 1 over 64. All right, so you really have to be fluid about moving between the 3 dimensions. To get from dimension 1 to dimension 2, we square. To get from dimension 1 to dimension 3, we cube. If you have to go in the opposite order, the opposite of a square is a square root, and the opposite of a cube is a cube root. Let's flip over and do some practice. All right, here we go. Let's get some practice going. Example A. The cans shown are similar with a scale factor of 67 to 100. When it says that there's a scale factor, remember that solids are similar if their linear measures are proportional. So when given a scale factor, you are given a linear measure. So this 67 to 100 is the linear scale factor. I like to write mine as fractions. Next piece of information, the surface area and volume of the smaller can are 40.73 inches squared for surface area and 17.16 inches cubed for volume. So here's the given information. Our job is to find the surface area and volume of the bigger can. All right, well, we cannot compare this linear measure to either of these values. This linear measure is a one-dimensional measurement. This area measurement is two-dimensional. This volume is three-dimensional. before you can set a proportion up, you have to be in the same dimension. So to solve for surface area, we need to turn our one-dimensional ratio into a two-dimensional ratio. To do that, we square. 67 squared over 100 squared is, it is going to be a big number. Check this out. 67 times 67 is 4,489. 100 times 100 is 10,000. This is the ratio I can use for surface area. Now, the ratio to use for volume goes back to the linear scale factor, but this time we cube it. (67 times 67 times 67), 300,763. 100 times 100 times 100 is 1,000,000. 1, 2, 3, 4, 5, 6. Now we have the scale factors that match the problem. So now I can set up my proportions. Let's work on our surface area proportion first. The surface area of the small can is 40.73. We're trying to find the surface area of the larger can. I'll call it X. We now have a ratio to set area to. Small on top versus large on bottom. This algebra should look pretty familiar to you. I'm going to cross multiply. 40.73 times 10,000 is 407,300. So I would have 4,489x equals 407,300. To get x all alone, I need to divide by 4,489. X equals 90.73. Now, what were we solving for? Because we're using this ratio, we're solving for area, so that is inches squared. That is the surface area of the larger can. Okay, I'm going to split my space here. I'm going to split colors too, so I can see volume now. Next, I need to set up a ratio for volume. I've got volume 1 at 17.16, and I'm trying to find volume 2. Here's my ratio for volume. 300,763 over 1,000,000. 1, 2, 3, 4, 5, 6. Now I need to cross multiply. 17.16 times 1,000,000. 1, 2, 3, 4, 5, 6. So I get 17,160,000. And to get x all by itself, I need to divide by this 300,763. Final volume, 57.05. And that is a cubic measurement, so I choose inches cubed. Whew, that's a tough problem to start with. I'm glad we did it. You guys, the key is making sure before you set up your ratios that you're in the right dimension. All right, let's get another look. Example B. The pyramids are similar. Pyramid P has a volume of 125 inches cubed. Pyramid Q has a volume of 64 inches cubed. Find the scale factor, that means linear, from P to Q. All right, so let's go back and write some stuff down. The volume of the larger pyramid is 125 inches cubed. The volume of the smaller pyramid is 64 inches cubed. The question wants to know the linear scale factor. Okay, so here I can write up a scale factor of cubic measure. That would be 125 inches cubed versus 64 inches cubed. If I need to get to a linear scale factor, I need to drop the cube. So I'm going to cube root each of these values. My little phone calculator has this feature on it. Maybe yours does too. If you're using a classroom calculator, you'll certainly find this feature. Cube root of 125 is 5. And cube root, clear that out. Cube root of 64 is 4. Because I'm working in linear measure, I know that these are in inches, not inches cubed. Okay, I'm going to do a couple more with you, and then we're going to practice the rest on our own. So let's check out this next example with the cylinder. Okay, let's start with our directions. Cylinder A is similar to cylinder B, which is not shown, with a scale factor that's linear of 1 to 2. Find the surface area and volume of B. All right, let's start with the scale factor piece. Our linear scale factor is 1 to 2. We're asked to find a surface area and a volume. So I'm going to have to change my linear scale factor into a ratio for area and a ratio for volume. In order to make a ratio for area, I need to square the linear value. So 1 squared over 2 squared, I'm writing kind of small, sorry about that, is 1 to 4. And 1 cubed for volume over 2 cubed is 1 to 8. Okay, switch colors. I'm going to start with surface area. Surface area of the smaller cylinder is 150. Surface area of the larger cylinder is what we're trying to find. When I set up my ratio, I have to match it to the area ratio, 1 to 4. Now I can cross multiply and solve. Take a moment and solve for x. Okay, so let's see my work over here. I did a cross multiply. So 150 pi times 4 is 600 pi, and 1 times x is 1x. So I divided by 1, which really doesn't do anything, and I've got x equal to 600 pi. That would be the ratio of that would be the surface area of cylinder B. Now I'm going to do a separate setup for the volume. The volume of cylinder A is 250 pi. I'm trying to find the volume of cylinder B. Since this is the volume measures, it has to be set equal to the volume ratio of 1 to 8. Now take a moment and solve for x. How did you do? When I completed my cross multiplication, I got x equals 2,000 pi. Because I'm working in the third dimension, I know that that's the volume measurement and that represents inches cubed. So here are my two measurements for cylinder B. Okay, I'll do one final example with you, and then I want you to try the last two on your own. Let's get started. Cone A is similar to cone B. Cone B is not drawn. The scale factor of A to B is 5:2. That is our linear scale factor. Find the surface area and volume. Okie doke. So, first things first, let's make up our three ratios. If the linear ratio is 5:2, then the area ratio is the square of 5 over the square of 2, which would be 25:4. The volume ratio would be the cube of our linear ratio. So the cube of 5 over the cube of 2, which would be 125:8. Now, using these three ratios, we can find the missing surface area and volume. Let's start with surface area. The surface area of the first cube of cube A is 2,356.2. We're trying to find the surface area of cone B. We can set this ratio equal to the area ratio of 25:4. Okay, I'm going to pause the video and solve for x. Okay, so how'd you do there? I set up my two fractions, made them proportional, cross-multiplied, and got 376.992. Now, because I'm working with my area ratio, that is my surface area. I also went ahead and set up my volume fraction here. The volume of cylinder 1, or cylinder A, over the volume of cylinder B, which is what I'm trying to find. And I set that equal to my volume ratio. I'm going to pause the video, and I want you to solve for x. I got a final volume of 476.9 centimeters cubed. Okay, what I want you to do is try to set up and solve both C and D. The next time I start the video, I'm going to have all my work up here just so we can compare answers. Okay, let's check your final work here and see how you did. The fifth example on your page says the solids are similar. Find the scale factor. This means you're finding the linear factor. They gave you volumes, so your volume ratio is your cubic measure. To go from volume to a linear ratio, you have to take a cube root. So I took the cube root of 8 pi and the cube root of 125 pi. That reduced to 2 pi over 5 pi. I left it in exact form since they gave me exact form. And then finally, the last example, the solids are similar. Find the scale factor. So again, the linear ratio. And this time they gave me the area. Well, I started with just trying to take that area and take a square root of it, because to get from area to linear, you take a square root. But this gave me a bunch of decimals. So then I started thinking, well, maybe I should reduce this ratio first. So I started reducing it down, and the furthest I could reduce it is 16 over 9. When I take the square root of 16 and the square root of 9, I get a final linear ratio of 4:3. Whew, okay, that's it for this lesson. If you need any help, let me know. We did not cover every single type of SOL question that you might run into. So if you have any questions along the way, come find me. I'd be happy to help, and happy studying.